So last time I ended with the hyperbolicity part, and this time I studied up to this logistic family and its relation to the Cantor set. And basically, they have the simplest case where the logistic family is just a function that depends on a parameter mu. And for mu in certain intervals, you have certain properties. And on the interval 0, 1, on the x-axis, you see that for mu greater than 1, then points outside of I, which they denote 0, 1, like fly out after one iteration. And if mu is greater than 4, there's actually some sort of Cantor set, essentially where points here, because when mu is greater than 4, then this graph is not restricted to less than 1. So this graph will be greater than 1 at some points. And then when you apply one iteration and apply it back to the identity map, then it flies out of I, and you don't want that to happen, probably because you want periodic points. So they kind of like have these two intervals, and for the second iteration, then you have another A interval. So it's like a Cantor set, except it's not necessarily the middle thirds. It's maybe some like 1/4 of the middle, or like some other fraction, or maybe it's irrational. I don't know. And they say that a set is a Cantor set if it's has these certain properties. And I guess that is like a characteristics of the Cantor set. It doesn't say that you have to define it in some way. And like, I didn't know that you could have a Cantor set that didn't remove just the 1/3. Like, doing some research, there's like a fat Cantor set where you remove only 1/4 of the area, and for some reason that doesn't have measure 0 or something like that. It's a non-zero measure. So I was thinking that there's some point between 1/3 and 1/4 where the measure jumps from 0 to 1/4. Because if you don't remove enough, then the remaining stages will not have measure 0, right? But apparently, like somewhere between 1/3 and 1/4, something weird happens. Maybe that's a bifurcation like from before. But yeah, essentially the Cantor set is it's self-similar. It's a fractal, which is what this book is kind of alluding to in the later chapters. And then the next chapter is symbolic dynamics. And at first, this doesn't make sense at all. Well, it doesn't seem like it's important at all, because it's just a bunch of sequences of numbers, right? And they define this norm, or I think no, the metric, which is basically if two sequences agree, they'll have the distance 0, right? That's what you want. And basically, whenever these two sequences, or two sequences you're comparing SITI, have different terms, in this case it's just 0 or 1, but if they have different terms, you take the place and then it's 1/2 to I. So like, so it's more important if they differ in the very beginning, because that will contribute more to the sum than if they differ in the end. So, which also makes sense because that's what you want the metric to be. And they define this shift map, which is essentially just removing the first term. And they prove continuity by, saying for every epsilon there is delta, using the distance that they have. So this is not just a metric on R, but it's like a metric on some other space, which is the sequence space, which is what they call. They have a lot of different properties, like that it's periodic points, like dense and other stuff. And now they have like topological transitively. I think they talk about it later, yeah. But the cardinality is 2 to the n, so because obviously periodic points will have repeating points 0 and 1, so 2, and it's dense, it has a dense orbit and stuff like that. But what it really gets interesting is the topological conjugacy, which is basically it relates to spaces, maybe spaces or dynamical systems. In this case, you really realize why they introduced a sequence space, because it's related to the Cantor set in the logistic, because there's some topological conjugate. Let me try to find it. There's topologically conjugate if there's a homeomorphism. And the homeomorphism that they kind of like alluded to was actually the S, which is or the sigma, which is the remove left shift. So And they say that when you compare it to the sequence space, it's a lot more easy to do dynamics or analyze the what's it called? What's this? I forgot what this was, what this Greek letter was, but basically you can compare two different dynamical systems, and you know that fixed points in one will be sent to fixed points in the other because it's a bijective map, and fixed points and periodic points in one will get sent to periodic points in the other with the same period, which is actually crazy because there's really not that much you can do with just like analyzing it if there's nothing nothing left that you should try. So you could like compare it to something else. And there's also semi-conjugacy, which is where H is not necessarily bijective, but just onto, so surjective. And basically, it's kind of like one way. So if you know about X, you know about Y, but not necessarily the other way around. So periodic points in X get sent to periodic points in Y or some other way, but you don't know the other way around. So that could also be helpful in the future. Yeah. That's it.